All right. So a lot of you have already turned in the midterm, which is nice. Any issues or questions about the midterm? Again, it's intended to be straightforward. Most problems you've seen before. It's hard to make it easier than that. Question? You can either type it or handwrite it. It doesn't matter as long as it's clear. You know, try to make it as clear as you can. Question? Define a what? Yeah, same format. Assuming that's what you guys want. You'll take another vote if you want in class, take home, but you know, probably guess which way that vote will turn out. But you know, yeah, you know, a multi-day window where you can work in it at your leisure for consecutive, say, 6 hours, and you get to choose, so you can arrange the time to be the most compatible with the rest of your schedule. You know, my gift to you, right? So it's highly flexible. Any other questions? Again, the goal is for everybody to do well and not be stressed out by having to memorize stuff. So, you know, open book is always a good thing. And it's problems that you've seen before, so that's even better. Okay, so last time we talked about push-down automata, and those are the machine model of context-free languages. For every context-free language is a PDA, a push-down automata, that accepts it. For every push-down automata, it accepts some languages also context-free. Remember, context-free languages are the ones that correspond to the context-free grammars. But it turns out that the machine models are equivalent. Just like for finite automata, we had the regular languages and vice versa. For push-down automata, we have the context-free languages and vice versa. So push-down automata is simply a finite automata with a stack. Everything else is just like a finite automata. There's states, there's start state, there's end states, state transition function that hops around between states as you process more and more symbols from your input. And here non-automatism matters. So then we proved some theorems, and we showed that the context-free languages are closed under union, and they're closed under clean closure. This was grammar-based proof, right? You can take two grammars. You want to create a new grammar that represents the language. It's the union of the languages of the two grammars, respectively. So take these two grammars, create a new start symbol of this new grammar that you're creating, and jump into the start symbol of these two old grammars. And now you just juxtapose, taking the combination of all of their rules side by side. Make sure you change the variable name so there's no variable name clash across the two grammars, obviously. And that'll get you to union. And clean closure, you just keep iterating like this with a new rule. Create as many start symbols as you want. Each one goes and generates something in grammar independently of all the other start symbols. And the story, that gets you to clean closure. But they're closed under intersection with regular languages because you can simulate a PDA and a finite automata using a cross product construction. Only one of them uses the stack, so there's no clash on the stack. Like if you try to simulate two PDAs, one tries to push, one tries to pop. What do you do as a simulator? It's not clear. And in general, you cannot intersect them and preserve context freeness. Now, it doesn't mean that it never works. It means it doesn't always work. So there's one closure property for finite automata that is broken here for context-free languages. That is closure under intersection, or under complementation too, because the two are related through the Morgan's law. Right? How do you understand all these theorems, the proofs? There's only a few people with any questions then. Should I repeat it? Should you have any questions? So to prove closure properties, you can work either with the grammars or with the machines. Take your pick, because we already know they're equivalent. Same as for finite automata and regular languages. But sometimes some proofs are easier, like the Morgan's law. So let's take that one. Why is it not closed under complementation? Well, it's not closed under complementation because we know it's not closed under intersection. And intersections are represented using union and complementation. 3 complementations and 1 union will get you the intersection by De Morgan's law. How many get that separately? Okay, that's true about any sets, not just languages, which happen to be sets also. It's a set identity. Well, so we know union preserves context freeness, but if complementation preserved it too, this whole right side will remain context free, but the left side is equal to the right side, and the left side is an intersection which sometimes isn't context free. So because union preserves, complementation must not preserve sometimes. That's a proof there, pretty straightforward, one sentence by De Morgan's law. How many get that? It's important that you get that. If 2/3 of you don't get it, ask me questions. Yeah. Sure. Yeah. So here we said that union preserves context-freeness. Why? Because you can jump from a new start state to both start states of the two old grammars, and that new grammar, the two old grammars juxtaposed together, plus this new start state that jumps to both, will get you the union of the two languages, right? So far, so good? How many say, yeah, so far, so good? Okay. So union preserves context-freeness. On the other hand, if you take the complement of two things and unioning them together, and you take the complement of that, that gets you the intersection. That's De Morgan's law for sets. And we already just said that union preserves context-freeness. So towards contradiction, assume that complementation preserves context-freeness too. So union does preserve. We just proved that. That's the first theorem here. But if complementation preserves also, A is context-free, B is context-free, so A bar is context-free by assumption. B bar is context-free because we just said by assumption complementation preserves. The union of two context-free is context-free by the first theorem, and the complementation of the union right there preserves also by assumption. So the whole thing on the right-hand side is preserved to be context-free, but the whole right-hand side is equal to the left-hand side, but the left-hand side is an intersection, and we already said that it's not closed on the intersection. And therefore, it can't be closed under union. Because if it was closed under both union and intersection, it'd be closed under, if it was closed under union and complementation, it'd be closed under intersection, because these two are equal. But it's not closed under intersection, so it's not closed under complementation either. Together they stand, together they fall, these two things, assuming it's closed under union. So that's, these two theorems together give you a much more encompassing meta-theorem. That's true in many other places besides context-freeness. So if some property is closed under union, but it's not closed under intersection, it can't possibly be closed under complementation either. How many get that? Now we're saying a much more general statement. It's not just about context-free language anymore. It's about closure under these three set operators: union, intersection, and complementation. If one of them breaks, another one of them must break too, together. How many get that? They're tied by De Morgan's law. Okay, does that make sense? Yeah. All right. What else? Any other questions about this? Again, all this stuff is in the book, spelled out with more words and so on, but since the explanations are so straightforward, if you can explain it in 2 sentences or 3 sentences, I think it's better that you kind of try to figure out those 1 or 2 or 3 sentences from scratch every time, rather than go down the list and memorize a list. Your intuition will be wrapped around it much more tightly if you kind of can regurgitate the reasons every time. Oh, okay, yeah, De Morgan's law. Together they stand, together they fall, intersection and complementation, assuming the union is preserved from the simple set identity. Okay, any other questions or issues? But you definitely should look at the book. How many people are looking at the book sometimes at least? Okay, that's great. If you never look at the book, I'm not sure why, but you should. Just to reinforce what we're saying here. Technically speaking, you don't have to, technically speaking, but it's just like technically speaking, you don't have to have a phone. But you'll be much better off if you do in some ways. Right? Okay, so we mentioned that certain things are decidable when you ask them about context-free languages, whether a language is finite or not, or the language of a grammar, or the language of a machine, and so on. Is it infinite? This here is parsing. We already mentioned that. Whether a given string is an element of the language induced by a certain grammar. There's a very famous piece of software that you use every day, that you probably use today, or at least this week, that answers this question. It's called what word? Compiler. How many get that? Any questions about that? Why this is a problem solved by every compiler? You have some grammar. What's the grammar? It's the rules of the language, the syntax, how you can form expressions with while loops and assignment statements and if statements and so on. There's a very definite syntax to any computer language. You have a set of grammar rules that allow you to generate and express things in that language. So does English, by the way, so does Chinese. Even natural languages have these grammar rules. They're just much more complicated than computer languages. Right? And there's also a lot of exceptions. But W here is your program. And whether your program is an element of the language induced by the grammar for C or C++ or Python or Java, whatever your favorite language is the question of whether that program is syntactically correct in that language. That's what a compiler does for you. That's what you do almost every day as computer scientists, right? But I'm also saying that some things are undecidable. And here are some examples. All these questions about either PDAs or context-free grammars, those are undecidable. Just so you don't think everything is decidable. But finite automata, a lot of questions are decidable. So for example, is a push-down automata minimal? Has the least number of states across all other push-down automata to still accept the same language? There's no way to solve that. Doesn't mean that you can't solve it in special instances. Just like you can solve the halting problem in very special instances, but not in general. Okay, and whether two push-down automatas are equivalent, whether a context-free grammar is minimal, the smallest number of rules or small number of variables, where the language of two context-free grammars is the same language, one is the same as the other, even though the grammars might be different. A lot of these questions are decidable for finite automata. We've already covered that. We gave algorithms for a lot of them, and but for PDAs, it gets to be much harder. Why? Because you got a stack, basically. The stack is unbound in memory, and it's hard to circumscribe all the possibilities. It could be arbitrarily long, lots of stuff on this stack. It's hard to capture all of that and enumerate all cases and so on, like we could with finite automata. Okay. Now let's prove a few more theorems in quick succession. How we get the hang of it. So if you have a two-way finite automata or a two-way push-down automata, that's more powerful than a one-way. And what do I mean by two-way? And by the way, the iconic language for non-context-free languages, we gave this example of A to the n, B to the n, C to the n. And we said A to the n, B to the n, C to the n right here. That's not context-free. We didn't prove it, but we just stated it. So it's important to know. You don't need exactly to know the proof for that, although it's right in the book. And basically it has to do with pumping lemma argument, just like for pumping lemma for regular languages. I remember the pumping lemma for regular languages to show that 0 to the n, 1 to the n was not regular. Okay. It's just a generalization of that to context-free language. It's a bit more involved because you got a stack going on or a grammar going on, but it's essentially a pumping argument involving a pigeonhole principle. So, but the bottom line is this language here is not context-free. There's no way to recognize this with a stack. Okay? So, having said that, we can prove a bunch of things. So, two-way PDA can be more powerful. Why is that? How would you, for example, recognize 0 to the n, 1 to the n, 2 to the n using a two-way PDA in one sentence? By two-way PDA, we mean what? The read-write head or the read head on the input can go left or right, not just in one direction like the definition says. Yeah. Yeah, so you can show that you can recognize A to the n, B to the n, C to the n. So one easy way to do it is push all the A's onto the stack, then pop against the B's. Then you'll know that they're equal number. And if they're not an equal number, you can reject right there and then because they're unequal, and so it's not one of those strings. Now go back across the B's, because you can go back now. It's got a two-way capability, so you can go back across the B's, push the B's onto the stack, and pop against the C's, and again, make sure those are equal number. And if everything checks out, you have the same number of A's as B's, and the same number of B's and C's, and by transitivity of equality, all three are equal. Because if something is equal to something, that something is equal to a third thing, all three are equal. Okay. How many understand that strategy? Okay, so if you had two-way capability, you can go back and pull some. There's many other ways to do it. It's not the only way, of course. All right, so that's an example of a non-context-free language that's accepted by a two-way PDA, but not by a one-way PDA. So two-way is a superpower with respect to PDAs, push-down automata. It gets you something extra, something more. For finite automata, no, it wasn't a superpower. Two-way finite automata can still recognize only the regular languages, not something else that's not regular. For extra credit, I ask you once to prove that. All right, what if you have two stacks? That's a superpower also. If you have two stacks, how can you recognize this language using two stacks? Again, pretty straightforward. One sentence. Recognize this language, A to the N, B to the N, C to the N, using two stacks, not one. Yeah. Yeah, exactly. Push all the A's on one stack, push all the B's on another stack, then pop both stacks against the incoming C's, and now they're all in equal numbers. End of story. So two stacks, superpower. In fact, for extra credit, show me that two stacks is not just a superpower. Not only can you recognize non-context-free things, but you can recognize anything you want, however complicated. You can recognize anything a Turing machine can recognize. Anything an arbitrary program can do, a two-stack PDA can do also. Extra credit, prove that. Question? All right. Next theorem. If you have one queue, that's more powerful than one stack. Why would a queue be more powerful than a stack? They're almost the same. I mean, what is a queue? Well, what is a stack? You can push and pop on one end, and it keeps going up and down, telescopes up and down like trays in a cafeteria. What is a queue? How is a queue different from a stack in that sense? It's not a trick question. Yep. Yeah, you push on one end, but you pop from the other. That's all. Instead of pushing and popping on the same end, you split it across two places. You push on one end, you pop from the other, and that's a queue. Right? Why would that all of a sudden be more powerful than a stack? How would you recognize this language with a single queue as opposed to a single stack? Because it's not context-free, so we know we can't do it with one stack, but how can we do it with a queue? Yeah, we have two places we can manipulate the memory. So can somebody expand on that a little bit and turn it into an algorithm to recognize this language? Yeah. Yeah, so there's lots of ways to do it, but one way is push all the A's onto the stack, onto the queue, or NQ all the A's. And then DQ one A at a time and flush a B every time you DQ an A, but don't throw the A's away. Every time you DQ an A, NQ it. Every time you pop an A, push it right back on the other end of the queue. And make sure you have a $sign that separates where the A's started and where the A's end. So when you push all the A's onto the stack, you say A, $sign when you finish with the A's. Okay? Or better yet, put a $sign on the stack first and then push all the A's. So you have $sign and a bunch of A's. The stack is really now a queue. So you have a $sign and a bunch of A's on the queue. Well, I'll write it down so it's not just words. Okay, so you have a $sign and a bunch of A's on the stack, which is now really a queue. Okay. Now, pop them against the B's, but when you do, put the $sign here, and whenever you pop an A, push it right back on the other end. In other words, you're not really flushing them. You're just taking them off one and putting on the other. And the reason there's a dollar sign here, so you'll know where it began and where it ended, where the beginning of the queue was, the first thing pushed, and you know, so you can encounter it later. In other words, you're cycling around the queue against the B's, and you flush the B's against the A's on the queue, but you don't throw them away. They're still on the queue. You're just cycling the whole queue over. How many get that? And you measure the number of A's on the queue against the B's in the input, one at a time, pairwise. Now when you get to the C's, do the same thing. All A's are still there. There's n of them. And so now you know there's as many A's as there were B's, as many A's as there are C's. All three are equal in number. And the story now you can accept, and you're good. If anything goes awry in this process, if you run out of A's on a queue and you still have B's, reject. If you have too many A's on a queue and not enough B's, reject. And so on throughout this process. Okay, so because it's a queue, you don't have to throw away something that you popped. You can push it right back on the other side with some separator marker, like a dollar sign or whatever. If you don't like dollar sign, use euro sign, yen sign, pound sign, whatever, or some other character. The point is, you can demarcate on the queue where is the boundary, and that boundary will keep shifting because you pop from here, you push there, you pop from here, you push there, you pop from here, you push there. By the time you see a dollar sign you're about to pop, you know that you went through the whole queue once. And if you still have B's left, there's too many B's, right? And conversely, if you run out of B's and you still didn't see the dollar sign, there's too many A's and not enough B's. How many get that? Only about half the class or third of the class. So is this process mysterious, or it's a pretty straightforward algorithm to match up the A's and the B's using a single queue? I mean, why are we even doing all this? Why can't we just enumerate? Why don't we just count the A's and say, okay, there's 37 A's, then count the B's and say there's 37 B's, and then make sure that that 37 is the same as the other 37, and now we know that they're the same number. Why can't we just do this? That's what you would do in your code, right? If I give you a file full of A's, B's, and C's and ask you to determine if that file is in this format, there's equal numbers of A's, B's, you count the A's, count the B's, count the C's, and compare the three counts and say yes if and only if. Right? Why can't you do this here? It's an interesting point. So it may not be finite. Will it be finite or not? It's a subtle point. Is n finite or not finite? It's finite. It can be very large. It can be a billion, a trillion, a Google, but it can go on forever, right? N is still an integer. An integer is finite. Yeah, you have no place to store the count. It's not because it'll be there's stuff on the queue, and even if there wasn't stuff on the queue, how would you count 1, 2, 3, 4, 5, 6, up to 37, or a Google, or whatever the number is? You'd have to count in some binary or base 10 or something else, and how would you do that with a single queue? Remember, it's not a register where you can take that number from the register, add 1 to it, and put it back into the register. That's not the kind of counting that this machine can do. In fact, a finite automata cannot do any kind of counting whatsoever. Right? It's not a proof, it's an intuition. The proof is, 0 to the n, 1 to the n is not regular, it's by pumping. The proof that a to the n, b to the n, c to the n is not context-free is again by pumping. But intuitively, where would you keep these so-called counts if you try to count all three quantities? You don't have registers that you can put arbitrary numbers in, right? So you have to do it the hard way. You have to use a queue as a counter, or a stack as a counter. Right? How do you get that concept? It's a restricted form of memory. It's like when you use an abacus, counting is a bit tricky. Now it's bound by the rules of the abacus and all these beads moving around back and forth and whatever the rules of an abacus are. It's not, you can't just take the number on an abacus, add 1, and, in one operation, without worrying about anything. Sometimes you'll have to move a whole bunch of beads to add 1 to a number represented there. And you have to do it according to restricted rules of the abacus with all the bees moving back and forth or whatever it is. Okay, question? Yeah, so no, you only have one Q. So you have one Q, and you push all the A's on the Q. There they are in green. Now, you see the first B. So you know you can stop pushing A's, and now you see the first B. So you pop an A against the first B, but you put it back on the end of the Q. The B goes away. You just flushed it. You saw it, you pushed an A, you popped an A, you pushed it back on the other side of the Q, and the B is gone because you move on. Now you see the next B, same thing. Next B, same thing. By the time you get to the end of the B's, and the Q was flushed exactly once all the way around. How do you know that? Because the dollar sign will come all the way around. How many get that part? The dollar sign will come all the way around when you flush the Q entirely because it was a dollar sign at the beginning of the Q. And every time you pop on one end and push on the other, the dollar sign now is not in the first spot, it's in the second spot. Every time you pop another A and push it back at the beginning of the Q, now the dollar sign is pushed to the third spot, and so on. It keeps getting shoved down. It shifts one spot at a time, right? But there's still a dollar sign where the beginning was, and by the time you get to the end of the B's, when you see the dollar sign in the stack, you know there's equal numbers of A's and B's. Otherwise, there's either too many A's or too many B's. And then you do the appropriate thing. If the numbers are unequal, you can reject immediately. If they're equal, you keep going. Question? I mean, there's alternate ways of doing it. So I'm not saying that won't work. So let's carefully think about what you're trying to do here. So you're pushing all the A's, and then you keep pushing the B's and pop one A every time you push a B. Well, I think that will work too. That sounds fine to me. Okay, I think I agree with that too. So he's saying that would be simpler than using a dollar sign. Okay, I mean, I can see that. So here's another algorithm. So his algorithm thing works also, and if it's simpler, let's see what the class thinks. You push all the A's, and when you see a B, you push the B, but you pop an A. Then you push the B and you pop an A, and you push another B and you pop an A. By the time you're done, you'll know that they were in equal numbers. Why? Because if you try to push a B and there's no more A to pop, there were too many B's and not enough A's. If you run out of B's and there's still A's to pop, too many A's, not enough B's, right? So by the time you're done, all the A's will be gone, and instead there'll be a bunch of B's there on the Q. Okay. Now you repeat the same thing with the B's against the C's that you just did with the A's against the B's. And if you do all that, and everything checks out, there's not too many of one and not enough of the other, accept, and it's a string of that form. Okay, I like that. That's simpler than mine. How many see that algorithm? That's pretty good. Extra credit for that. That is good. Yeah. And there's many other ways to do it too. Just like there's many ways to write a program that does a certain thing. Okay. Any other thoughts? This is not meant to be difficult. This is, using a Q to count things, using it as a counter. Which base is the counter in, by the way? It's kind of a subtle meta question. How many see that we're using a Q as a counter? Really? Only 10 people out of 100? How many see that to recognize if a string is of that form, you have to count A's, B's, and C's? How many see at least that? Okay. How many see that by doing it with a Q, we're essentially exploiting the Q to behave as a counter, counting things up? Good. Okay, that's better. You had me worried there for a second. All right. Now, the next question is more subtle. What base are we counting in? Base 1 in unary. It's not binary counter. It's a unary counter, base 1. How many see that? What is a base 1 counter? What is counting in base 1? It's a tally, exactly. So to give you a concrete example, somebody sees these cartoons, somebody's in jail, and they're marking the days they're in jail. How are they marking it? They're counting in base 1. There are as many marks as the count. So if they're in jail for 10 years, there'll be, 3,600 marks on the wall. How many get that? If they were counting in base 2 and they were there 10 years, how many marks on the wall is that? Roughly. How many marks are needed, the minimum, to represent the total count? Let me ask it that way. If they were there 10 years, they're counting in base 2. 1,300? Less than 15, but yeah, you're in the right ballpark. How many will it be, roughly? To get to 3,600 is 10 years times 365 is 3,600. To count to 3,600 in base 2, how many digits are we talking about, at most? What's the log base 2 of 3,600, roughly? Without using Google Calculator. It's about 12, maybe 13, right? 2 to the 10 is 1,024. 2 to the 12 is 4,096. This is only 3,600, so it is 12. So a little piece of advice. Know your powers of 2. You're a computer scientist, at least the first, 20 or so, roughly. You don't have to know them exactly. But 2 to the 10 is 1,024, right? It's 32 squared, right? 2 to the 8 is 256, right? 2 to the 10 is 1,024. 2 to the 20 is what, roughly? 2 to the 20 is what, roughly? Blurt it out. Do it quick. About 1 million. 2 to the 30 is what, quick? 2 to the 30, quick. 2 to the 30, say it loud. Don't be shy. 1 billion, yes. Why 1 billion, roughly? Yeah, another 1,000. So 2 to the 30 is like 2 to the 10 times 2 to the 10 times 2 to the 10. We just said 2 to the 10 is roughly 1,000. So 1,000 cubed is roughly 1 billion. So 2 to the 40 will be roughly 1 trillion. So, just ballpark. You don't have to know the exact digits in all these numbers. That's less important. But order of magnitude, you should know powers of 2, backwards and forwards in your sleep as computer science. Otherwise, you'll keep you'll keep hanging up on these things, and it'll stifle you, and you won't be able to compare things. And so then you have to sit and think. Instead of constructing algorithms, you'll be doing powers of 2 calculations, and it's not very effective. And it's not rocket science here. It's just, break it down into pieces, and you'll know the answer. Yeah. No, because the absence of a tick mark is, if you want to use a blank as another character, now you're in base 2. You have a character and a non-character. That's 2 characters. Also, it'll be very ambiguous, because this slide is full of non-ticks. So what is the real value if you don't know? Right? How many non-ticks are there in this area here? It's hard to tell if it's 1 or 10 or 100 or 1,000, whatever. So no, you just count the ticks. Okay, so now you know a little bit about why we count in base 2 and not in base 1. In base 2, how many digits you have to use if you represent a number of size k? The number is k. K could be 1,000, 1,000,000, 1,000,000,000, 1 billion, a Googleplex. That's k. How many binary 2 digits as a function of k? Base 2. Log. How many see that? All right, base 3. How many digits? Base 5, base 4, base 6. How many digits? These are my next 5 questions. Base 10, how many digits? The one that we know and love and use every day, right? That one. 10, right? Toes, also base 10. That's why we count in base 10. It's completely arbitrary. It's because we happen to have 10 fingers evolutionarily. If you were a lizard that only has 3 fingers, like one of those geckos or something, we'd be counting in base 6. And it'd be just as good as base 10. Base 10, how many digits to represent k? K is the value of the number, 1,000, a million, a billion, a googolplex. How many digits? Log, what about the log? Yeah, log of a different base, but still log. The answer to all these questions is log, 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 and log. All the bases, 2, 3, 4, 5, 6, 10, 20, 50, base 16, hex. All these are logs. Log's number of digits necessary. Log is a very small quantity as a function of its input. Right? Log base 2 of a billion, we already said, is 30. 30 is much smaller than a billion. So to represent numbers as large as a billion, we just need 30 bits, 30 digits. In base 10, we need log base 10, not log base 2. That's a little bit smaller number of digits, but still log. How many get all this? Seriously? How many get this? Log, oh good. So don't scare me like this. It's cruel. All right, having said that, base 1. How many digits represent k in base 1? Is it log? No. What is it? K. So that's a terrible base to use. You don't want to represent a billion using a billion digits. That's terrible when you can do it in 30. That's why we don't use base 1. We use the smallest base that makes sense in computers. Now you know. How many realized this before? Because we certainly don't use base 10 for computers, and there's reasons for that besides this. Why don't we use base 10 in our circuits? Yeah. So it's voltage on and voltage off, wax on, wax off. So it makes much more sense to map 2 voltages to 2 digits. But we can use intermediate voltages. We can use voltage off and on and voltage 1/3 and voltage 2/3 in between. And that will give us base 4. And similarly for base 10, we can use 10 different voltages. We could. We have, it's not hard to construct circuits like that. But what's the problem with that now? Why don't we use 10 voltages to represent 10 digits? Now our computers can count like we do in base 10. Yes, error correction. If a voltage gets slightly shifted higher or lower, now you don't know that it did. It looks like a different digit. But if a low gets to high or high gets to low, that's a very dramatic change. It's much less likely to occur. You've got to buffer against errors if you use 2 extreme values and 2 extreme values only. If any one of them shifts, it's still close to these one of the 2 extremes that it was before. And errors can be easily detected, corrected, and avoided. But if you use a whole range of different little things, one little shift, and you'll be over there in a different value, and you won't know it. And these errors can occur all the time for all sorts of reasons, including random fluctuations or quantum mechanical issues or gamma rays hitting your circuit or temperature variation or somebody sneezes and the circuit jumps or whatever. And that's why we use base 2, because it matches nicely high and low, and it avoids errors, and it's the smallest base that we can use and still get this efficiency, avoiding a tally base of base 1, where the number of digits will go exponentially, as opposed to logarithmically. Okay, so now you know why base 2, for all these good reasons, is the one we use in our circuits. Okay, so a queue is better than a stack. In fact, it turns out that a queue is as powerful as a Turing machine. A queue is not just more powerful than a stack, it has the ultimate power. It's incredibly more powerful than a stack. It doesn't just recognize this language, it recognizes any other language. It's recognizable by any Turing machine or any algorithm or any program that you can think of or anybody can ever think of. For extra credit, prove that. It's also on the problem sets. It's a problem. How many have seen that problem on the problem sets? Okay. If you have 2 heads on a PDA, you can recognize more things in context free. You can recognize this language using 2 heads, 2 read heads on the input. Still going one way, so it's not a two-way. It's not a two-way head. It's 2 one-way heads. How do you recognize this language here? A to the n, B to the n, C to the n, using 2 heads going the same way on the input. Again, an easy question. Yeah. Turn an automata into a queue? What kind of automata are we talking about? Yeah, so a queue, just like a stack, is an unbounded storage. You can push and push and push and have larger and larger queue, and there's no end to how much storage. It's not infinite, but you can just keep growing it and growing it, so it's unbounded memory. A finite automata has a finite number of states, and that's it. Whether it's 17 or 1,000, it's still finite, and that's all you got. So you cannot implement an arbitrarily large queue using only 17 states. Eventually, you'll run out of states. Because if you want a queue larger than 2 to the 17, how are you going to represent it using only 17 states? You can't. So a queue is more capability than a finite automata has. Finite automata is a fixed memory. A queue is arbitrarily large, potentially, if you keep pushing and pushing and storing stuff away. Now, our machines in our pockets and on our desks, do they have unbounded memory or bounded memory? Are they more like finite automata, or are they more like Turing machines or PDAs or arbitrarily large queues and stacks? The machines that we know and love that are in front of you right as we speak and in your pockets. Are those more like finite automata or Turing machines or PDAs? Or what do you guys say to that? How much memory do they really have? Unbounded or finite? How many states can your machine be in? How many different pictures can possibly appear on your screen for all eternity? How many different pictures can appear on your screen? Finite or infinite? How many say infinite different pictures can appear on your screen? Infinite number of different pictures, images appear on your screen. Whatever your screen size is. How many say it's finite? Good, it is finite. It's not infinite. Why is it finite? Why can your screen show a finite number of possible images and nothing else beyond that, ever? Not now or ever. Yeah. Yeah, there's a finite number of pixels, like 1,000 by 1,000 pixels, 1,000,000 pixels, let's say. Each pixel could be on or off, or maybe one of several colors. That's still a finite number of combinations per pixel. It's a finite number of pixels. You can multiply it all out. It'll be a huge number, don't get me wrong. It'll be huge. Very large number, but it'll be finite. And after that, there'll be nothing new you can ever display on your screen if once you display all these things in all possible combinations. How many get that? Good. I mean, it doesn't mean computers are boring. That means there's also a finite number of movies you can ever see, or a finite number of novels of 1,000,000 words or less. How many get that? That doesn't mean you'll ever, in your lifetime, run out of movies to see or books to read. The point is, there's a finite number of each of a certain given size, even if the size is large. I don't want to discourage you with that, revelation, but it happens to be true. So you should know it. So back to your computer. Is it finite automata, or infinite memory, or more like a Turing machine, or more like a push-down automata, or what do you guys say to that now? The computer's right in front of you. How much memory do they have? Finite or infinite? How many say infinite memory? How many say finite? Yeah. If it was infinite, you couldn't buy it for $3.99 at Best Buy. Think about it. Yeah, it's all finite stuff. All of our machines are, no matter how big or small, I mean, some of them are large and have lots of memory, and that includes the disk, by the way. It's not just the RAM that we're talking about. It's not just the screen. It's not just the registers, the CPU. It's the entire disk and everything else in there that can store state or information or bits. So your computers right in front of you are finite automata. If you didn't know that before, now you know. And the languages they can recognize, regular languages. How many realized this before, by the way? A few of you. Okay, well, now the rest of you know. It's interesting. Now, having said that, how many states can your finite automata in your pocket or on your desk be in? How many different states can it be in? Roughly. Take a wild guess. 2 states, 10 states, 1,000, 1,000,000, a Google. One for each core? One for every core in a CPU? Okay, let me back up. Maybe I was presumptuous. What is a state? Before we count states, let's say what a state is, so then we know what we're counting. So if your computer is in a different state than their computer, but they're both Mac PowerBook or whatever it is, PowerPro, what makes that computer in a different state than that computer? I mean, I see a lot of you have this exact same Apple machine. If anything is different on yours than on theirs, a single bit even, not all the bits have to be different, just a single bit is different, it's a different state than the other machine. How many get that? And where are those bits? Either on the screen, in memory, in RAM, on disk, in the CPU, in the register, I don't care. One bit different than the bit on their machine. It's in a different state. All right, now we know what states are. How many are there on your laptop or your smartphone, roughly? Just take a wild, arbitrary, ballpark guess. I don't care about exact numbers at this point. You know, you can, if you're off by 100 orders of magnitude, that's still close enough. You see how easy it is to answer that. Yeah, it's 2 to the number of bits. It's the exponential of the number of bits you have total. On your hard drive, in your RAM, how many bits roughly do you have in this thing? 500 gigabytes, maybe a terabyte for some of you if you have bigger disks or whatever. So it's 2 to the billion. And that's bytes, by the way, so you have to multiply by 8, because 8 bits in a byte, so it's 2 to the 8 billion if you have a terabyte sitting there in front of you. 2 to the 8 billion, is that bigger than a Google, smaller than Google? I'm going to say it's bigger than a Google. It's not just bigger than a Google, it's unbelievably bigger than a Google. All right, so now you have more perspective on comparing these things and relating these results to what's sitting in front of you and hanging out in your purses and pockets, smartphones and so on. And those are finite automata with very large state sets. Now, because they have so many possible states, it makes them quite interesting. It's not like the finite automata has 3 states and recognizes, A star, B star. Otherwise, you wouldn't be paying $1,000 and carrying them around. It wouldn't be doing much for you. But they have so many states that they can be and do quite clever things for you, quite complicated tasks. So in some sense, they're almost like Turing machines, almost like arbitrary computers. In fact, they are computers. But technically speaking, they're finite automata. And technically speaking, they can only recognize and process regular languages, not even context-free languages. Never mind arbitrary languages. But because they have so many states, it's not obvious everything we just said. Right? All right. So 2 heads are more powerful than 1 head. How do you recognize this with 2 heads? There's 2 heads pointing to the input, but there's still 1 stack with 1 head on the stack. Good question. Maybe somebody new. The same 3 people, 5 people keep impressing me, and I appreciate that. But maybe somebody else take a chance, feel the rush, the adrenaline, speak out loud, take the chance, and you'll come out a hero, whatever you say. But maybe you'll be right too. On top of that, somebody new. Don't want to call on people. Don't want to put people on the spot, but volunteer. What's the question? The question is, here's a language. It's not context-free, but if you had 2 heads, 2 read heads on the input, you can recognize this language with a post-run automata with 2 heads. That's the question. The question is, how do you do it with 2 heads? Yeah, you could do all that, and that would work. Let's try to answer that without using the stack at all, ignoring the stack. Yeah. Yeah. So take the two heads, take one of the heads, move it to the end of the A's, the beginning of the B's. And now walk across the A's and the B's in lockstep with the two heads, making sure they're an equal number, and either one has more or less. Now the first head will be at the end of the A's, beginning of the B's. The second head will be at the end of the B's, the beginning of the C's. Now what? Same thing. How many get this algorithm? Good. That's a lot of people. I appreciate that. Thank you. See, you said it so obviously that everybody understood. That's great. That means it's a great algorithm. We didn't use this stack here. So what happened? We didn't use the stack, so is it still context-free, this language? This PDA was modified to have two heads, so it's not exactly context-free. I mean, it wasn't context-free before. It's not become context-free now. We recognize it with two heads. But we didn't use a stack. So that means that two heads are even better than a stack in some cases. Two heads can do what a stack cannot. How many get that? So now we have a comparable comparison between a pair of heads and a single stack. And certainly two heads are better than one. Did you hear that before? Two heads are better than one. It's a famous saying. Now you know why. That's why working in groups is a good thing. So we just proved that two heads are better than one. But we proved it without using a stack. So we proved another theorem. What's the subtle theorem that we proved without actually saying it yet? We just proved that with two heads, you can recognize this non-context-free language without using a stack. So there's another theorem here that's not written on the slide. We just proved it too. Try to look at the big picture. There's a hidden theorem we just proved. What is it? We use two heads but no stack. No, but it's a very good try. Not if they can only go one way. So we use two heads but no stack. What kind of a machine is with two heads and no stack? It's a finite automata. We used a finite automata to recognize this non-context-free language as long as it had two heads. So what's the theorem here? Let's just say it. Yeah, so a two-headed finite automata is superpowered. It can do stuff that a one-headed finite automata cannot do. For example, recognize this language. And this language is not just not regular, it's not even context-free. So a two-headed finite automata can do what a one-headed push-down automata cannot do. That's how much more power is two heads than one stack. How many get this? Good. Very good answer. All right, so finally, non-determinism also increases the power of push-down automata, and there are languages that you can recognize with a non-deterministic push-down automata, but not with any deterministic one. And I'll just give you an example. It's not trivial to prove, so we won't prove it here necessarily, but the language WWR, in other words, the set of all palindromes. You have a word and a word reversed, palindrome. There's a PDA that can recognize palindromes. That's non-deterministic, but there's no deterministic one that can do the same, turns out. Okay. We won't prove that there's no deterministic one that can do it, but let's prove very simply that there's a non-deterministic one that can do it. How do you recognize palindromes with a non-deterministic PDA, push-down automata? One stack, one head, recognize all palindromes. How do you do it? You can start pushing the W onto the stack, right? And it's in reverse order, so now you can pop it against the other WR. So if the two were separated, let me give you a simpler question. Let's say it's not quite a palindrome, it's a palindrome that looks like this. Not arbitrary palindromes, but palindromes where the middle is demarcated with a special character, so you know where the middle is because you'll see this green dollar sign. So it's palindromes where the middle character is green, but the rest is just a palindrome. Flip it around, it'll read the same way. A man, a plan, a canal, Panama. There's a palindrome sentence. Check me on that. It's true. Just happen to know it. So how do you recognize palindromes with the middle marked specifically? Yeah. Push the W until you get to the middle, and then pop against the WR. So when you get to the middle, to the green symbol, to the green dollar sign, you'll know when to stop pushing and start popping. And if you push and then pop, and then you make sure that they're equal, identical pairs, good. You got a palindrome on your hands. How many get that? Pretty straightforward. All right. Now let's take the dollar sign away. If you take the dollar sign away, and it's just WWR, no dollar sign. How do you know where the middle is? Short answer, you don't. So what do you do? Give you a hint, use non-determinism. What's your answer? What do you do about the middle stuff, the middle business? Non-deterministically, try every single character as if it was the middle and branch in all directions. And one of them, if it was the middle and your guess was correct, one of them will succeed in verifying that that was the middle and pushing against the popping and equal numbers and meshing the W against the WR. You'll succeed and then you'll declare victory. But all the other ones where you were wrong or you failed, what about those branches of computation? Short answer, they don't matter. As long as you succeed once, the whole thing is fine. That's the definition of non-deterministic acceptance. You just have to succeed once. Doesn't matter how many times you fail. It's like venture capital. You found 20 companies, 19 failed, doesn't matter, because the one that succeeds becomes Google or Apple or Facebook, pays for all the failures. Right? Question? So, very good question. How does the stack work in this non-deterministic scenario? Every branch has its own stack. It's independent of all the other stacks. It's like copies of the stack, but they're independently pushed and popping separately than all the other copies, and they don't commingle. You can't have one branch check out the stack of the other branch. It's like reality splitting, and every parallel universe has its own stuff going on, independent of the others. What about finite automata? Every finite automata has a context-free grammar, but every context-free language has a context-free grammar too. So some context-free languages are regular, right? Give me an example of a context-free language that's also regular. Anybody? Yeah, I mean, any regular language is automatically context-free. That's a theorem. Why is that theorem true? Any regular language is also context-free. It's not, the reverse is not necessarily true. So somebody prove that every regular language is a context-free language as well. Yeah, you can have a PDA recognize whatever the finite automata recognize. Why is that true? Why can a PDA do exactly what the finite automata does? Exactly, because the PDA is a finite automata with a stack. So have the PDA not use its stack, don't touch its stack, leave it alone, as if it wasn't there, and now it's a finite automata. So that means that every regular language is also a context-free language, but not every context-free is also regular. That's not true. 0 to the n, 1 to the n is context-free, but it's not regular. By pumping, we showed that it wasn't. So you have to be careful. Any questions about any of these? So we proved a bunch of theorems in quick succession. A lot of them are in the book. Most of them are actually on the problem set, so I just solved a bunch of problem set questions for you too. And none of them are particularly long or complicated. You just have to kind of wrap your mind around what's going on, think about it a little bit, and you know. So I guess no extra credit there because I just solved it. So okay, so the pumping lemma for regular languages, we talked about that before, but there's an equivalent version for context-free languages. We already mentioned that. It's a little bit more tricky, but You can look it up. It's not worth going through in class and wasting a lot of time and having you still not quite get what's going on because it's tricky. So here's what we just said. Every regular language is context-free because you can construct a grammar that simulates it, or simply use a PDA without a stack. And then some context-free languages are not regular. We already saw examples of that: 0 to the n, 1 to the n, right? So it's proof by pumping argument. So have we talked about the pumping lemma in general? I think. Okay, so all right. If we haven't, I thought we did, but if we haven't, okay, let's do it now. Okay, let's try to nail that one down. I keep referring to pumping, but okay. So why is this language not regular? Intuitively, you can do it. We can do it with a stack, right? Count the zeros by pushing them under the stack. Pop against the ones by popping them against the zeros. As ones come in, pop them. Flush the ones against zeros being popped from the stack, and then you'll know they're an equal number, right? So you use a stack as a tally, as a counter, okay? A regular, a finite automata cannot do that because it doesn't have a stack. That's not a proof. It's an intuition. Regular languages are much simpler than context-free languages. Finite automata cannot count arbitrarily high, and these counts will get arbitrarily high. So another way of intuiting it, why a finite automata cannot do this, count the zeros and then compare them to the ones, is that a finite automata only has a finite number of states, like 10 states or 17 states or even 100 or 1,000 or Google states, but only a finite number. And if it has 10 states, what's the largest it can count if all it did was counting? If it had 10 different states. It'll be like 2 to the 10 if it's non-deterministic, right? If it was deterministic, it'd just be 10. If it's non-deterministic, it'll be 2 to the 10 because we're in a subset of the states. But you cannot count beyond 2 to the 10 if it only has 10 states. Each state is either in or not, even if it's not deterministic, so it's a bit in some sense. You're either in that state or not in that state, 2 choices. Same for the other states, same for the other states. How many combination of states you can have? As many subsets as there are in k states, that's 2 to the k. So 2 to the k for a fixed k is nowhere near as large as n for arbitrary n. Right? So finite automata cannot count intuitively, but that's not a proof either, because maybe there's some other way of doing it without counting. Right? Because if I wanted to recognize a language that looks like this, 0, 1 star, there's several ways to do it. One of them is count all the zeros, count all the ones, make sure they alternate, and if all these conditions are true, you got it. How many see that algorithm? Okay. There's another way of doing it. Look for a 0, 1. And when you find it, okay, look for a next 0, 1. Then look for another 0, 1. Now you don't have to count all the zeros and all the ones because you can eliminate them in pairs. And that saves you the trouble of counting all the zeros and counting all the ones. You could do the counts and that'll nail down this language, but you don't have to because you can just eliminate them in pairs and keep. How many see the point here? So counting will suffice to recognize this language in red, but it's not necessary. So maybe it's the same thing over here. Counting will suffice to recognize 0 to the n, 1 to the n, but maybe that's not necessary either. Maybe there's a clever way to eliminate zeros against ones without counting. Then you don't need a stack, and then, well, maybe this language will be regular after all. Question? Creating a grammar? Oh, so you can create a grammar, and that will make it context-free. That'll establish, if you create a grammar for this, and by the way, let's, since you said it, let's create a grammar for this. S goes to what? 0, S, 1, or empty string. Here's a grammar for it. That grammar, once you convince yourself that this grammar generates this language, the grammar says it's context-free because the grammar exists. In fact, not only exists, it's on this slide. Even if it wasn't on the slide and it exists, it'd still be okay. That means that language is context-free. But that doesn't answer the question of whether that language is also regular. Just because there's a grammar for it makes it context-free, but doesn't make it non-regular automatically. Because I can give you a grammar for a regular language too. I can give you a grammar for this language. Here's a grammar for this language here. S goes to S 0, 1, or empty. So this grammar, this context-free grammar, will generate this language. How many get that? So does that mean that language is context-free? Yes, it does. Does it mean that it's not regular? No, it doesn't. How many see all of that? Any questions about that? So just because there's a context-free grammar for it doesn't mean it's not regular. It means it's context-free, sure enough. It doesn't mean it's not regular. Right now we're trying to show that this language right here is not regular. And a simple grammar for it doesn't cut the mustard. Because here's a simple grammar for this regular language. So context-free grammar doesn't mean it's not regular. It means it's context-free, but it doesn't mean it's not regular. Any questions so far? So why is this not regular? We can't just say, oh, because finite automata cannot count arbitrarily high. It's true, but it's not a proof. Maybe some clever way to count that you haven't thought about. All right, here is a proof. Let's say, towards contradiction, there was a finite automata that recognizes this language. Let's say there was a finite automata that recognizes this language. And it takes a string of this language that's very long. Longer than the number of states in this finite automata. So let's say this finite automata had 5 states, and it supposedly recognizes this language. So it has 5 states, and it's supposed to recognize this string here, 8 zeros followed by 8 ones. It's one of those, right? It's supposed to recognize, but it only has 5 states. But this string is of size 16. So the machine, supposedly, that recognizes this language will look at this string and go, okay, state, start at the beginning, start state, then change state, then change state, change. Finally, okay, accept. Let's say it does this job as advertised. It recognizes all strings of this form, 0 to the n, 1 to the n. So let's say you just recognize this string. This machine that started at the initial state and keeps changing states, by the time it goes pretty deep into this string, after a while, what can you tell me about its behavior? It keeps changing state, but it only has 5 states. This string is 16 long. What can you tell me about something non-trivial about what it would do or not do along the execution path? Never mind exactly what it is. Maybe somebody, yeah. One state, at least some state will repeat, and perhaps more. How many see that? At least some state will repeat. 2 words. Why? Pigeonhole principle. Good. See how much mileage you're getting out of principle. It comes in handy right here and many other places. Pigeonhole principle, 1 state will repeat. So the computation will cycle on itself, right? You'll start somewhere at the begin state. You'll take some path to some state, and then some loop will repeat, and finally you'll take some path to a final state and you'll be done, right? So this red loop is the thing that repeats. How many get that picture? Why? Because it has less states than this size of this string. And if it had more than 5, let's say it has 20 states, make this string 50 long or 100 long, longer than the number of states in the machine. Force the machine to loop on one of its states at least. Now, if this machine loops, and over here, this path here was some substring u, and this path here was substring w, and this substring here was some substring v. In other words, the characters are from this state to that state along this path together, concatenated together, is the substring vu. This characters here from here to here was w, concatenated all these characters along this path. This path can be short, this path can be long, it can be 1 character, 1,000,000 characters, doesn't matter. This loop here, all the characters around that loop together concatenated is v. Let's call it the substring v. Now, if I take this, so the complete string that we fed into this machine is UVW. So this thing here is a UVW. right? So U, V, W is equal to that blue string down here. How many get that? I'm just labeling things. That's all I'm doing. I'm calling this a U, this a V, and so now the U, the V, and the W are together, together, this string here. And the V portion is the one that caused me to loop. Why? By the pigeonhole principle. So if I take a string U, V, V, W, what can you tell me what this machine will do with that string U, V, V, W? Not one V, but two V's. U, V, V, W. What will that machine do? Accept or reject? How many say accept? How many say reject? How many say accept? Why? Yeah. The U will get you here, the V will get you here twice, and the W will, it's deterministic. It ain't going to do anything it didn't do before. Seeing the same input as before, it'll do the exact same thing. That's what makes it deterministic. Right? So U, V, 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 W will also accept. So not only will accept U, V, W, it will accept all U, V to the I, W for all I. Any power of V in the middle there, as long as there's a U at the beginning and a W at the end, any number of V's in the middle will cause it to accept also. How many see that? So you'll accept an infinite number of strings with arbitrary number of V's in the middle for any number. Will it accept no V in the middle? Will it just accept U, W, no V? How many say yes? Just a U and a W, no V. How many say yes? How many say no? How many say yes? Is it by my tone of voice that you're deciding if it's true or not? Why would it, anybody want to argue, why will it accept or not accept UW, no V? Yeah, you don't have to go around this loop. You can go U here, then followed by a W, and that'll get you to the final state. It's deterministic. It doesn't need to cycle a bunch of times on that V state, on that red state there. So yeah, so 0 is included. So that's why it's greater or equal to 0, not just greater or equal to 1 on the number of V's here. Right? There'll be 0 or more V's, and all of them must be also in the language. So what are we saying? That if you have a string long enough in the language, you must also have an infinite family of strings in the language based on some substring called V that can be pumped up as many times as you'd like, and no matter how many times you pump it, it'll also be in the language, right? So that's called the pump. That's why it's called the pumping argument, because you can take some substring and pump it up, and you must remain in the language. That's true about any regular language. Any regular language. It's got to be, if there's a long enough string, you can take some portion of it. I'm not saying which, I'm saying it exists. I'm not saying every single portion that you take will have this property. I'm saying some portion must have this property. Others may not. But this property must exist for some substring of a long enough string. How long enough string should we take for this to kick in and be true? How long should this string be? Longer than the number of states, great. Longer than the number of states of the machine. Which machine? Whatever machine accepts that language. Take the number of states, take a string longer than it, and this thing will kick in with a vengeance. So here's the finale. So ask yourself, so somewhere in here there must be a pump, a pumpable substring. If the pumpable substring is only on the zeros, pumping it up will not keep it in the language because you're only pumping up zeros and not ones. Similarly, the pump cannot be only on the ones. Because if you pump up only ones, it'll be too many ones, not enough zeros. It cannot cross the zeros and the ones, and those are the only three types of pumps you can have. Only ones, only zeros, or ones and zeros crossing the boundary. Pumping up this will get you zeros and ones in the wrong order, right? Because you have zeros, ones, and zeros, ones, zeros, ones, you pump it up. Here you have too many ones, too many zeros when you pump it up, which means this string cannot have a pump. But we just proved that every regular language, there must be a string long enough that must contain a pump, but this one is long enough because it's bigger in a number of states, and it can't possibly contain a pump, which means this language is not regular. How many get this proof? Good, good. All right, we'll pick up exactly there when we left off next time.